we've done phase difference, and now we're doing path difference. So the way to think about it is path difference is an expression of how far ahead or how far behind one wave is from another, okay? And it creates a path difference. And path difference is subsequently expressed in either meters as a set distance or as a fraction of a wavelength, because when you measure the distance between two peaks on a wave, you have a distance. So effectively, that means that you can express path difference as a physical distance or as a fraction of a wavelength. And the path difference and phase difference sort of work together, because path difference sort of creates phase difference, and that together, when you put those two things together, lead you to different kinds of interference. And interference is a topic that we're going to be exploring in a fair bit of detail in videos further along in this series. But for now, take a look at the tutorial video where I talk to you about the maths behind path difference. So, we've discussed phase difference, okay? Now let's talk about path difference. Now, I like to say, personally, that path difference, okay, creates phase difference, okay? Because if phase difference is how in or out of step waves are, path difference is effectively how far in front or how far behind one wave is from another. So if we imagine this situation where we have this wave and then we have another wave which starts, let's say we extend this and we have another half wavelength here. Let's say it starts here and we have that, okay? This wave has started at this point and this wave has started at this point. So there is a path difference, there is a path difference here, okay, which is equivalent to a half wavelength, right? But there is also, as a consequence, a phase difference, okay? We've got total destructive interference. There's a phase difference of 180 degrees, right? So path difference is in effect what causes phase difference when we're talking about two separate waves, okay? And when the path difference is equal to a whole number of wavelengths, right? So 1 wavelength, 2 wavelengths, 3 wavelengths, where the path difference is a whole number of integers. I can draw that for you now, right? Well, he says I can do it. Okay, there we go. There. Yeah? What you notice is that those waves actually line up really nicely. Okay, so when the path difference is equal to a whole number of wavelengths, then you have constructive interference. However, when the path difference is equal to a half number, of wavelengths, then you get destructive interference. Okay, so what we need to understand is kind of this idea that path difference creates phase difference, okay? And the relative phase difference between waves is what's going to affect whether they interfere constructively, resulting in amplification, or destructively, resulting in, I suppose we can call it degradation. But this idea that phase difference and path difference are kind of inextricably linked is very important to understand. So the best way to do it is to do practice and to kind of, try and draw these waves. How would a wave look if it had a path difference equal to 1.5 wavelengths, for example, or if it was 3.5 wavelengths. Just have a look and see what you can come up with, and it will start to come together piece by piece. So that is path difference. Hopefully you can see how that ties into phase difference. If you haven't watched our previous video on phase difference, I recommend that you go and check it out. It's linked in the description. Also, please like and subscribe. I know I say this every single time, but it really helps the channel grow and helps us get more quantum content to you guys. If you have any questions or any videos that you'd like to see, then again, put them in the comments, and then we'll pick up on those and try and make that for you. But in the meantime, stay quantum, and I'll see you soon. Bye.